Picking back up in multivariable calculus, we're in lesson 15.10 on our first day. We've talked about changing variables and that Jacobian matrix that we just worked out. My goodness, if we can make a substitution of variables, then very nicely what we're going to be able to do is use that Jacobian inside of the integral, and you can see we've written that off to the side here. And as we change our variables, we'll have a brand new integral, a brand new interval, and brand new region to graph over. So we're going to revisit example 1. We're actually working backwards. We started with that square region and we transformed it into this region with parabolas on our side 2 and side 3. Ironically, what if we start with those parabolas? What if we actually had these parabolas given to us, y squared equals 4 plus 4x and y squared equals 4 minus 4x? Everything is graphed out the way you see it right here. We can work this integral out much the same way that we have before. However, we're asked if perhaps we could go ahead and make a transformation and use these substitutions right here. If so, we could most definitely get some assistance and get some help. The Jacobian, as we're looking at this, it's going to be, as we're looking this over, it's the derivative of x with respect to u. And if we take our derivative of x with respect to u, we'd get 2u. Then we take our derivative of x with respect to v, that would be negative 2v. In our second row, we're taking the derivative of y with respect to u and the derivative of y with respect to v. Well, that's going to be 2v as we take our derivative with respect to u, and then we'll have a 2u as we take our derivative with respect to v. And as we just do a little cross multiplying, we'd have a 4u squared minus, and multiplying here, we'd have a 4v squared, a negative 4v squared, pardon me. You can quickly see that your Jacobian is going to be 4u squared plus 4v squared. So here's what we're getting at. We could very quickly take this integral right here and say, you know what, we're going to go ahead and take this y of 2uv, but then we're going to have our Jacobian. Our Jacobian is what we said we had right here. Here's our Jacobian. It's 4u squared plus 4v squared. And then we'd have a du dv. But guys, look at this. If we made a transformation, look at this. We're integrating our u from 0 to 1. Likewise, we're integrating our v from 0 to 1. A much, much easier integral to work out. So, look, if we were given that guidance to make those substitutions, that could really assist us significantly. We're going to have an 8u to the third v plus an 8u v to the third. And then we'll go ahead and take our antiderivatives. First, our antiderivative with u. Bump that up to a 4 and divide by 4. We'll have a 2u to the 4v. Bump this up to a 2 and divide. We'd have a 4u squared v to the third. Then, of course, we're going to evaluate that between 0 and 1. The 0 is going to wipe everything out nicely. So when you plug in a 1 for your u's, I think you can quickly, even just doing this in your head, see that you'd have a 2v plus a 4v to the third. Of course, you could go step by step and show those substitutions and work it all out. But then what? Well, as we take our antiderivative with respect to v, we'd get v squared plus v to the fourth, evaluating between 1 and 0. Plugging that 1 in, we'd get a 1 plus 1. And then, of course, we'd subtract, and final answer is going to be a 2. So, again, if you see that can be exceptionally helpful and nice. Let's take a look at something that you have seen in the past, changing with the RD theta. We justified that, we proved that. But my goodness, we can also show that the Jacobian will allow us to go from rectangular to polar. When we're going to polar, we had x was equal to r cosine theta. We had y was equal to r sine theta. And really, the Jacobian is allowing us to change variables. We're changing from an x and a y into an r and a theta. So if we were to apply that, just want to show you a partial derivative of x with respect to r. Well, we just have a cosine. That's what we'd see right here. What's our partial derivative of x with respect to theta? Well, the derivative of cosine is negative sine, so we'd get a negative r sine of theta. And then we do the same thing right here. The derivative of y with respect to r, well, that would just be sine of theta. The derivative of y with respect to theta, well, that's r cosine theta. And then you cross multiply and subtract. You get r cosine squared minus a negative r sine squared. Minus a negative turns into plus a positive. Factor out that r, and I think you're going to see very quickly that cosine squared plus sine squared is just a 1. So your Jacobian is r. And that's what you're seeing right here. And then you have your dr d theta. So just wanted to show you what you've been seeing so very frequently is in fact valid even as you approach it from the Jacobian.